now it's got some distributing or different pieces on both sides of the equation. It's often a good strategy to rewrite it and put it in the standard form. So not 100%, but if you're unsure what to do, that's not a bad approach, and will eventually get you to the answer. And once it's in standard form, our goal there is factor. Remember that a quadratic equation is any one that has an x squared term. It doesn't have to have an x or a constant term, but it has to have an x squared term. And you know, when you're setting these up, we would often prefer that that x squared term is positive, given the choice, right? I prefer to have a positive a there versus a negative. It's going to be easier for me to factor, right? Because that's my next approach. I want to factor, then I want to set each factor equal to 0 and solve. Okay. So that's our strategy with quadratic equations right now. Let's see an example. Okay, so here's an equation that we're trying to solve. And this is a little bit what I was talking about. This doesn't look like that standard form, and so I'd really like to get it into standard form. And you might be saying, but look, this is factored, right? X times x plus x minus 3, that is factored, but it's factored equal to 18. That's not helpful. I need it factored equal to 0 in order to use this technique where we split it up. So I do have to go ahead and rearrange this. Right, I distribute that and I bring the 18 over, and now it's in that standard form, and now I'm in a good spot to factor it. Right, since it's a trinomial, we do that. We play with the factors here: 1 and 18, 2 and 9, 3 and 6. And again, once you've done enough of these, you're going to start to even recognize a lot of them, because there are finite combinations, and you've probably done a pretty big proportion of them already, right? So if we let one be minus 6 and one be 3, now we can take each of those and set them equal to 0. And solve for our two solutions, right? And with quadratics, we are always looking for two solutions. It's true that sometimes the two solutions are really the same number, in which case there's only one distinct solution, but we should always get two sort of equations or two possibilities whenever we have a quadratic. So that's something to keep in mind when you're thinking about what your solution or answer to the problem might look like. With a quadratic, you should be getting two solutions. Any questions on this problem? Okay. Just a couple things to watch out for. For some reason, I often have students that have trouble with this kind of problem. I think they see the x squared and they want to try this strategy where they split it into these two factors, but it's not actually a trinomial, right? There's only two pieces here, and then maybe they think of the binomial strategies, right, where you try and factor the two pieces, but it's not that either, right? Really what you want to do here is pull out the GCF first. So sometimes students, you know, we tried to encourage you to use the GCF last week when we met, but it's a little rusty sometimes. So you do need to look for that GCF. And when you have it factored like this, there's really three factors here, right? There's the 3, the x, and the x minus 3. So technically, you know, if we had 5 factors, we'd want to figure out if any of those factors could be 0, because if any of them are 0, then my whole problem is 0, right? And I've got a solution. What you can see there quite quickly, of course, is that 3 never equals 0. So that constant factor doesn't give me any solutions, right? If there's a 3 or a 10 out in front, that's not going to give me any solutions. So I can ignore that. But the x here certainly does give me a solution, right? If x is 0, then this whole thing is 0, and I've got a solution. So that's one answer. And then of course here is sort of more traditional, right? Which tells us that x equals 3. Questions on any of those problems? You're all very quiet, so I don't know. Is this easy or hard or? I will have to assume, guess off of previous experience. My guess is that if you've done the work on factoring, that is the hard part of these problems, right? Factoring is the sort of, you know, kind of new thing. That the rest of it is pretty straightforward if you get it factored. Okay. However, there's always usually questions when we get to the application problems. There are a couple kind of different varieties, but let's say the area of a rectangular let's make that a rectangular parking lot. Is 84 square meters, and the length is 2 meters less than twice the width. Find the dimensions. Messy handwriting, but so this is an application problem, and it is just like all of our other application problems that we've seen in the course and the application problems that you're going to run into in the future, in that you want to start by defining the variable, making sure you really understand the question, define the variables, and then use that to help you come up with an equation. Once you have the equation, you're going to solve that equation. And that's where the type of equation is going to matter. The setup part, it doesn't really matter whether it's a system or a linear or a quadratic. You're just going to set it up by sort of defining and structuring the problem. And then it's the solving it where you're going to use the particular techniques, whether that's quadratic or a system or whatever it might be. So I've got some rectangular parking lot. The area is 84 square meters, and the length is 2 meters less than twice the width. So, you know, standard approach, I don't know anything about width, so I'm going to let that be W. And then I have a length, right? The length is 2 meters less than twice the width. So I want to write that down. I want to define the length. So remember with systems, we may have wanted to define these as two separate, I guess we haven't, sorry, I'm jumping the gun here on the systems. We haven't, we talk about systems. Yeah, we did. Sorry. I had a little panic there that we hadn't talked about that yet. But yes, like when we solve systems, we had some applications and we would have two variables, and that is okay. But given the choice, we'd really prefer to have one variable. So here, you know, the length is L, but the length is 2 meters less than twice the width. So, right, 2W minus 2 meters less than twice the width. And so now I can set up an equation. Now that I've got the pieces defined and written down, I can set up an equation that the area is equal to the length times the width. And what we can see here is that this is generating a quadratic equation. So now is really the spot where I say, oh, okay, that equation is a quadratic, because when I multiply the W and the 2W, I'll get a W squared. So that's a quadratic. So that I'm going to solve by factoring. You could move the 2W squared and the minus 2W over to this side, but then I get a negative. I like to have a positive, remember, on my W squared. So I'm going to move the 84 over to the right side. And here you can either approach this by noticing there's a GCF of 2 and factoring that 2 out. Or you could also think about dividing both sides of the equation by 2. That would also eliminate that 2. Either way, that 2 is not going to generate any solutions. So I don't need to worry about it in terms of my solutions. I need to factor this other part. That's a trinomial. The difference is just 1. So I'm looking for two factors that are very close to each other, right? And the two factors have to be 6 and 7. Minus 7 and plus 6. I don't need that anymore, right? W minus 7 is going to give me one answer. And W plus 6 will give me another answer. Now, with application problems, both of these numbers make this equation true. But both those numbers do not make sense in terms of my model and my actual problem. So with application problems, you're really going to want to make sure that you'll often only get one solution. And it also turns out that often the negative solution doesn't make sense because you're dealing typically with a real thing, right? We don't often represent those with negatives. So my answer here is 7. But just like anytime I do an application problem, I want to go back and make sure I've really answered the question. The question said find the dimensions. So I can't just say W equals 7. I should say it's 7 meters wide. The length then is 2 times 7, or 14, minus 2, which is 12. So it's 12 meters long. Right, and when I grade these and when I work through, when I look at these, I am looking for something like this where you've defined the variables in some way. Sometimes that's a little sentence, but sometimes it's just like this, like I can label the picture and that's enough to define the variables. And then I'm also looking for the equation. Right, and then of course, finally, I am looking for the correct answer. So you're going to get points if you make it to any one of those stages. Question? Any questions? Okay. All right, so if there's no questions, I'm going to assume that means that it's going well or that you're done with the section 4, or mostly done. And so let me take the last little bit here to talk about some rational expressions, which is section 5, right? So just preview some of the ideas there to get you off to a good start. So a rational expression looks something like this. Rational, remember, means like a fraction in math. And what we're talking about typically here are fractions of polynomials. Now, they look a little complicated. There's certainly more to write down than just a polynomial, because you got a numerator on the top and a denominator on the bottom. But the good thing is they still work the same way that fractions do. So for instance, if you saw a fraction that looked like 12 over 8, probably your first instinct would be to reduce that. And you might not write it out quite so formally as this, right? Where you factor both the top and the bottom and then cancel that common factor. You'd probably think of it as maybe as dividing top and bottom by 4, but it gives you this reduced or simplified version. And so that's exactly what we want to do with this rational expression as well, right? We want to make sure that it's simplified. The most important thing, and this is why I no matter what, I was going to talk a little bit about this section before you get started. The most important thing about rational expressions is that you factor before you start to do anything. If you don't factor before you start to simplify or add or subtract or any of the other operations, you're going to get the problem kind of 100% wrong, and it's going to look bad, right? So if you start by factoring, you'll often stumble towards the right solution, even if you kind of make some errors or aren't totally sure what to happen, right? So just really, before I do anything here, I'm not going to mess around there. I cannot cancel the x squareds because it's not factored, right? It'd be like, it'd be kind of like, I mean, I know if there are many people who sort of feel this, there's an x squared on the top and bottom, so I'm going to cancel it. To me, like that's almost the same as being like, there's a 2 here on the top and the bottom, so I'm going to cancel the 2's, right? No way, right? That 2 doesn't mean the same thing. It's not a factor. You would never consider canceling those 2's. It's the same idea here. We cannot cancel these until I have factored or broken this down. I know that some of you, it still might, may not be able to move directly there so quickly, perhaps, but you could get there, I think, with our factoring strategies, same strategies that we're using before in section 4. Now that it's factored, I really want to see this kind of the same way that I see this. I got to cancel the 4's because they were exactly the same, right? One on the top and one on the bottom. So the same thing here, right? I get to cancel those x plus 2's because it's factored, and I have the same expression on the top and the bottom. The x minus 3 and the x minus 2, those are different things. So I cannot cancel those. I have to keep those separate. They're not the same. Don't get fooled by the x there. Think of it as being enclosed with the parentheses, right? X minus 3 and x minus 2. And that's what I'm looking for when I try and simplify an expression. It turns out that if you're asked to multiply or divide, those operations are actually very similar to simplifying. There's a little bit extra to them, but basically they also just come down to factoring and then canceling the common factors. So when I teach this, and if you look at the lecture videos, I will group these three things together because you should really think of them in the same general strategy, right? If I want to simplify or multiply or divide, I want to factor. I want to do that with every rational expression, but I also want to just factor and cancel. So for instance, if I have to divide, let's try 3x over x squared plus x squared minus 9, and let's divide that by x squared plus 2x over 5x minus 15. Okay. So here we have two rational expressions and we're dividing them. I still am going to want to factor. So the 3x is already factored. The x squared plus 9 is this. This, the top one, be careful, that's that GCF factoring we did before, and the bottom is also a GCF factoring. And so what we want to do is remember when we divide fractions, we end up multiplying by the reciprocal. And that's the same operation we're doing here with polynomials. So this is going to become 5x minus 3 on the top and x plus 2 on the bottom. When you multiply, you just get to multiply straight across. So all of these are going to be factors in the numerator and all of these are going to be factors in the denominator. And I'm going to get to cancel anything that's a common factor. So I can see there's an x minus 3 between the top and the bottom. This is 3 times x, and this is x times x plus 2. So those x's get to cancel as well. And I just have to keep track of what is left. 3 times 5 is 15. X plus 2, x plus 3. No need to multiply those out in the bottom. It's not wrong if you do, but it's not going to improve your answer. So certainly more steps, right? You got two rational expressions. You have to do a little flipping and combining. But in the end, all you are doing is you are factoring and you are canceling. Questions on either of those examples? Okay, I'll keep asking just in case. Okay, so simplify, multiply, and divide, I'm grouping all together that is a single basic strategy or a single approach. And then there's two other types of problems in this section. I'm going to just focus on the next one, which is to add and subtract. So remember, if I'm going to add and subtract fractions, if I want to add those together or subtract them, I need to have common denominators. And in order to see what's needed with the common denominators, we really like to factor the denominators. And now I can see, I could have seen it before, right? But now I can see that this denominator has an extra factor of 5. So I'm going to multiply top and bottom here by 5. So I'm creating the common denominator. Then I have 5/10 plus 3/10. I get to add those together over that common denominator, which is 8/10. Once they're added, now I can try and reduce that a little bit too, right? Clean things up a little for my final answer, which would be 4/5. Same strategy with polynomials. So I still want to factor, but I'm factoring with a different goal. My factoring is not to cancel. My factoring is to create a common denominator so I can add them together. Okay, so that's why this gets a sort of different category. Let's try 2 over x squared minus 25 plus x over x squared minus 9x plus 20. Let's keep it simple. Let's just make that a 5 up there. So what's important here is that we recognize the plus. That tells me, of course, it's addition. Addition means common denominators. In order to get the common denominators, if we were in class, I would ask you to all answer me together in unison. When you are looking at a rational expression, you have to start by factoring, right? So in order to get the common denominators, I need to factor these denominators. If you don't factor with numbers and you end up with like 20 instead of 10, you'll still get the right answer in the end. It'll take you a tiny bit more work, but it's not really a problem. But if you do that here by sort of not factoring and just multiplying both sides by the other denominator, you're going to get a really big, messy numerator that you may not actually be able to solve or figure out. So you really have to get in the habit of factoring. That's a minus. X minus 5, x minus 4. So just like the last problem, now I can see what's missing when I look at these factors. This one has an x minus 4, so I need an x minus 4 over here. All right, if I do it on the bottom, I have to do it on the top. Over here now, I have x minus 4, x plus 5, x minus 5, so I need an x plus 5. Now I've created the common denominator, so my next goal is to go ahead and combine the numerators together. So I've got to make sure I don't cancel here. I want this to all go together now. So this is 2x minus 8 plus 5x plus 25, which is the same as 7x plus 17, and that's all over this. So that's this. That's like the 8, and it's all over this x minus 4, x plus 5, x minus 5. Just leave that denominator. There's never a case where you want to multiply that out. That's a lot of extra work. And I would kind of like it if something canceled here, but the 7x plus 17 can't get changed, and that's going to give me nothing to work with, right? Nothing to cancel. Okay.